Okay, so hi everyone. Thanks for coming at the last talk of the day. Hopefully you keep it lively and keep people excited. So today we're going to talk about facilitating the integration of quantum computing into smart grid infrastructure. This is a joint project with Alona on stage with me now, Jeanette Miriam Lorenz, and as well as Philipp Hernrecht, who was our master student from LMU Munich, Fraunhofer, and was working at E.ON. So to set the stage a little bit, for those who were in the talk I gave earlier, I'm sorry for the repetition, but I have to explain what E.ON is in case you don't know about the energy sector. In a nutshell, E.ON is one of the largest utility providers in Europe. We serve energy to about 47 million customers across over 15 different countries. And we have basically 1.6 million kilometers of electrical wires in Europe, which we monitor. That's the key number for this talk, actually. And we also have about 1 million renewable energy connected assets in Germany alone. And this nice video on the right-hand side, you see the yellow dots. This is a time series throughout the day where you see local renewable energy being generated in Germany. And the red is the local energy demand. And so we're going through a digital transformation of the grid where instead of having a few connected parts, so to say, that are heat and power plants that generate electricity by burning gas and spinning turbines, we're moving towards this decentral digital aspect. So we need to use all this yellow on the plot. The energy demand in the future is just increasing more and more. So it's really, really important to make use of this in smart ways. And now the twist comes that when you're feeding in electricity to low voltage grid, which is what connects to this building, you have to monitor what's going on. So are you going to fry the power lines, let's say? And currently, this is not really monitored at that scale anywhere, actually. So we usually monitor the sort of high or the medium voltage lines, right? So you do power flow and things like this. And so this is part of this observability problem is, can you, number one, optimize this amount, as well as make sure that the power grid is safe? So this is what I was just talking about in a cartoon diagram. You have the mid-voltage grid feeding down to the low-voltage grid. You have some kind of community buildings, maybe some solar panels on some houses with electric vehicles plugged in. And it's sunny in one part of the grid, it's rainy in other parts of the grid, and each time as the weather changes, you have a different amount of power flow flowing through the lines with uncertainty. And what you want to do is measure on each parts of the line, what is the current live voltage running here? Can you predict what this is? And if you put sort of PMU sensors everywhere, you want to measure what the kind of live power flow is. Now this is very difficult to do, both physically and also from a data perspective, because we have 1.6 million kilometers, yeah? And this is the big question is, how do you measure and compute these power flows and the kind of grid state? And this is one way to do it. So you can do it with classical machine learning, where here this is a electrical engineering diagram. You have a power line, and you want to predict what the current and what the voltage is on each parts of the line. From that, you can calculate the resistance of the line and other electrical engineering parameters. So you could measure this with sensor data, train a machine learning model classically, and then you want to do the classical time series prediction that says, here's the voltage over time with this much uncertainty. There's some recent evidence in the quantum machine learning community that you may be able to get sort of soft skill quantum advantage where you could get more accurate solutions or need less training data and things like this. So one of our ideas was, let's replace the classical model with a quantum machine learning model in the middle of this pipeline. Let's train that in the cloud, because you have cloud access to quantum compute. And then let's copy this into what's called a classical surrogate. So can you extract so you use the quantum computer to do a better job at learning the data, and then you extract the core essence of that model in order to deploy that classically at many different places. And this is one way to sort of get access to the power of quantum if you can prove that you get an advantage in training and you want to duplicate this model classically. And there's many challenges to this problem, how to do it, and for the rest of the story, I hand over to Alona.
Thank you. All right, let's dial back and talk a little bit about quantum machine learning. So if you're part of the club, you're very well aware that this is an incredibly rapidly developing field. So even if we compare to the state of the art that we had, let's say, 3 years ago, it's just incomparable to what we have today. It's incredibly fascinating to be a part of, just to see how much the ideas are morphing and approaches are changing, which is also kind of hinting that actually we might be close to finding like this very thought for quantum advantage. On the other hand, we also need to remember that if we think of all the keynotes we heard today from a lot of quantum hardware vendors, we also see that the roadmaps that they're proposing today beating our expectations from the previous years. So let's say, for example, like IBM today's proposed that by the 2029 we'll have the first access of the early fault-tolerant computers, which is incredibly exciting, meaning that we might be very close to finding the application, the quantum algorithm that would be helpful for the industry. Amazing. But can we actually do something about it with today's technologies that we currently have? And if we talk to any application guys, which is the majority of people attending this summit, which is amazing, we actually discovered that there are there's like a very major bottleneck to deploying any quantum solution in a production pipeline, which is pretty much the limited on-demand access to quantum hardware. What that means is that a lot of hardwares that are available today are hosted in the clouds, often by international companies, which means that, let's say, if you handle sensitive data, like, for example, E.ON, you have to be very careful to know the whole pipeline that your data goes through, all the way, every server that it actually bounced at. At the same time, if you want to run some real-time applications, and you've tried that with a quantum hardware, you know that you're probably going to end up in a waiting queue, which kind of defeats the purpose of it being real time. And if you're also doing something like many requests to quantum hardware, you're also going to run a pretty high check. Now, especially talking from a standpoint of this panel, the general quantum stack, especially from a algorithmic side, can we actually do anything about it? Turns out the answer is yes, if we exploit certain aspects of quantum circuit behavior. Now, if we look under the hood, if we look at the quantum circuits that are popular today, especially within the quantum machine learning community, we see that if you have a certain quantum circuit that encodes classical data, that measures expectation, or that computes expectation values in the end, and preferably also encodes your data in a repetitive manner, your quantum circuit starts exhibiting a periodic behavior. If you have a periodic behavior, you can start to apply quantum Fourier analysis to it. This is the idea that was proposed by the paper from Maria Schuld. Also, if we start applying Fourier analysis, we can gain some insights into the model. Like, for example, if you want your model to exhibit interesting properties, or being able to represent rather complex functions, it really much depends on the complexity of the embedding you use. and it's very much preferred that you actually layer it in multiple layers. Now, if we can apply a Fourier analysis, we can also represent our circuits with a Fourier series. This representation through the Fourier series has been coined as a classical surrogate. It originated by one of the groups here in Berlin. And the idea behind this approach is actually quite simple, or it's rather straightforward when you see it. It's not that easy, probably, when they come up with it. So the idea is that you have a Fourier series, and you want to replicate the output of your quantum circuit. So based on the structure of a quantum circuit, you can already compute all your frequencies that this one can exhibit. Now the question is, you need to find the coefficients of your Fourier series. So you just pack it in this linear equation, you solve it, you find your optimal coefficients. Within this, and it's going to be important in a second, within this system, you also can build like a matrix of all your exponentials, which is, of course, makes the solution slightly easier for representing. However, again, this is why it's so great to actually have summits like this, because you actually see how people who try to implement things that have been developed in the lab actually on the real use cases and see how well that behaves. So this approach sounds incredible, and we tried it out. The problem is that if you look at the matrix A, and you start thinking about actual sizes, actual scales, you really quickly realize that the space that you need to store this matrix A is scaling with exponential scale. So for example, here is a very simple representation, and honestly, this is optimistic. So like how many, let's say we have from 5 to blah blah qubits, and here we see that already at size of 25 qubits, which is way lower than any industrial utility, we are already requiring at least an HPC system, and very quickly we're running out of memory even on an HPC system. Well, this is actually not great at all, because we just need to, just 25 qubits is not enough for anything. So the question is, can we do something about it? And the answer is yes. So in the joint project between E.ON Digital Technologies and Fraunhofer AKS, we looked at the problem. We looked at the we analyzed exactly the use case we're looking at and the method we're trying to utilize, and we found out that actually, in most cases, first, you don't need an absolutely perfect replica of your quantum circuit. Secondly, you don't need it to be a perfect replica for absolutely any use case. And thirdly, if you just actually reduce all your redundancies to the bare minimum, you can still get away with negligible loss, like reconstruction loss. However, for example, I will show you in a second, our proof of concept implementation, we required like a tiny fraction of a previously required memory. And what is more, our method scales linearly. So, see, here, I mean, this is like a little bit of an estimation, even up 50 qubits was just still below the industrial utility, but we're still way below the HPC capacity limits, and yeah, we still have a lot of space before we reach it. Now, let's talk about our method in action. So here we actually try to build the whole pipeline. We concentrated on a 9-qubit quantum model, which was trained to predict the net hourly electrical power production and usage from one of the power plants from E.ON. So this model has been, we've created this model, we trained this model. Of course, it's important to realize that if this classical, the existence of classical surrogates also impose the limit on when the quantum advantage can potentially take place. And the answer is it's during the training time, not the inference time. So once we've trained this model, we've created a classical surrogate. This classical surrogate has been created by one of our master students, so Philip, going to use him in the beginning. It was done on a normal laptop that you just have for work. And previous approach wouldn't require at least a solid working station, so it would have required at least 10 terabytes of memory. Of course, even by IBM predictions, with the fault tolerance, this is a perfect simulation, this is not noisy, so even by IBM timeline, we will see some fault tolerant qubits, potentially around 29, which means we still want to know how well this thing behaves in the noisy environments. We don't want it to live in a vacuum. So yeah, we also actually tried it on a real hardware to see what happened. We had to scale it down a little bit. The reasoning is mostly that just training a model on a quantum device requires some tricks. And it's also a bit expensive, so we wanted to pre-train it on a noisy simulator. That's why we had to scale it down. No other reason, just to make sure that this is said. So 4-qubit quantum model that was pre-trained on a noisy simulator that was then finished training on the IBM Kyiv chip, and with just slightly over 1,000 data points, we managed to create a surrogate that achieved the mean square reconstruction error of 0.0013. Now, what does it actually mean? So this means is that there is a way that we can actually deploy our quantum solutions into productions. This method is, easier, because the classical, this Fourier representation of the surrogate, this classical surrogate idea, once it's created, it's very classically computationally easy to compute. So if you have edge device, your Raspberry Pi, anything, you can deploy it on anything you want, on any premise, within your electrical grid. We enabled it to be way cheaper, so you actually, you do not hit the classical limit yet with your quantum solutions. And what's more, even though this has been created and developed for a specific use case, the method itself is not use case specific and can be used for any industries from energy to mobility and healthcare. Thank you so much. Please feel free to reach out to Corey or me if you have any further questions, or shoot your questions. Thank you very much.